One of the great things about the course is everybody's coming from lots of different backgrounds. I hope at least some of you are sort of, let's say, computer scientists that may not have thought about, that might be thinking about robotics a lot, but maybe haven't thought about dynamics a lot. And some of you are mechanical engineers or aero engineers or otherwise sort of very familiar with dynamics. If that's the case, then I hope still I'll say something a little bit different about the way that, different than the way you normally think about dynamics. The goal for today is to make sure we're on the same page. We all understand sort of the basic concepts that we're going to use in the course for nonlinear dynamics. But really the goal is to sort of stoke your intuition and make you think about the dynamics the way I hope you're thinking about dynamics in the course. I want you to love dynamics, okay? So we can actually do a lot of it if we think about even just the dynamics of the simple pendulum. We're going to spend a lot of today thinking about just very simple systems like the pendulum. So let's start by drawing our simple pendulum here. So simple, when you're thinking about these models, there's lots of things that simple might mean, but simple typically means you're using point masses instead of sort of inertial models. So I've got literally a pendulum with all its mass concentrated at the end of the pendulum here with an ideal rod of length L, and I'm going to parameterize it with the coordinate theta from the bottom, and I've got gravity pointing down and mass M, and basically the simplest possible robot I could ever describe, right? Because it's so simple, we can generate the equations of motion in a heartbeat. So the total energy of that system is 1/2 mv squared, which is v in this case is L theta dot, so L squared theta dot squared. That's my energy. The total potential energy, it's sort of weird. I'll make it a negative energy just because it's hanging. I'll have zero potential being at the sort of at the base there. So I'll do negative mgl cos theta as my total potential energy. And if, like I did in the appendix, which I don't expect you to be able to do, but I just want you to know that it's easy to do if you want to. If you want to get the equations of motion, the differential equations that describe that system, you can just assemble the Lagrangian, which is t minus u. You can pump it into the Lagrangian differential equation. That's a dt partial L partial q dot I minus partial L partial q I is some general force I. In this case, we just have one q, right? So in this case, our q is theta and q dot is theta dot, right? And we get out the equations of the pendulum, which is gives us ml squared theta double dot plus mgl sine theta equals this q. Q is sort of a generalized force, a force input in generalized coordinates. So when we're thinking about pendula hanging down like this, we're going to think about a couple different sort of generalized forces we'll put in the system. We'll put a torque at the base here, a torque here, and we'll think about a damping too. So for in our case, we'll say Q is going to be some torque input. We'll just call it U directly. That's what we've been calling our inputs to the system. And then we're going to think about some damping, some friction in the system, because if you have a real robot, you're going to have some damping there. And the simplest model of friction in this case would be which would be a linear function of the velocity. We'll do more complicated models later, but this will be our damping. This will be our input u or tau. So if you have a motor at the base. Okay, so in total, we'd like the equations of motion we're going to think about today to be this sort of canonical ml squared theta double dot plus b theta dot plus mgl sine theta equals u. This is our canonical pendulum differential equation. Okay, so you've probably taken differential equations, and you know that the standard thing to do once you're given a differential equation, if I have my canonical differential equation here, it's a second order differential equation, ml squared theta double dot plus b theta dot plus mgl sine theta. I'm just rewriting it at the top here for you. Okay. Then the standard thing you do in your DiffEq class would be to solve the differential equation, right? So solving the differential equation means if I give you the initial conditions, for instance, in this case, I'd give you theta at time 0, right? And I'd give you theta dot at time 0. Then what I'd ask from you to solve the differential equation is I'd like you to give me theta as a function of time, right? That's the standard ask for a differential equations course. So unfortunately, the answer to this question is relatively unsatisfying. Okay, so this is really one of the simplest differential equations I could write down, and I can't. Well, I sort of can solve it, but you wouldn't like what I'd write down, and I can only solve it if b equals 0. And when b equals 0, I have to use elliptic integrals of the first kind, and it's just not useful. And then if b is not equal to 0, I can't even give you a closed form answer. Okay, so what the heck? I thought it seems like we've solved more complicated differential equations than that in your DiffEq class. But the big difference is the fact that this sine theta entered in there. So it's not a linear differential equation, it's a nonlinear differential equation. And it's not meaningful to solve. It doesn't have a closed form solution in the general case using within closed form. So that's a bummer. It seems like we're hoping to do more complicated robots than this, and already we're stuck. But it turns out you can still do a lot of things with this, of course. So one of the messages for today is that I can basically completely understand the behavior of this system, if I'm willing to ask slightly different questions. Okay, so asking exactly where theta is at time 6.2 is sort of not the right question. That's a hard question to answer. But if you ask about what theta is as time goes to infinity, or what are the basic properties of a solution of theta, there's lots of things we can answer and can answer meaningfully, but it's just not using the traditional solve that differential equation tools. Okay, so that's what you have to get used to when you start doing the nonlinear differential equations. You have to start using different tools, right? So for instance, if I take this system and I ask you what is theta at time infinity, what would you think is the obvious answer? Yeah, it's down at 0, right? Especially if b is greater than 0, right? If I've got some positive damping in the system, then eventually I'm going to run out of energy and stand still. You all know that. And we're going to have lots of ways to compute that as using sophisticated tools for more sophisticated equations. But we're going to do it we're going to see for a class of differential equations, there's very intuitive tools that we'll use today in lecture to make sure we're all on top of it. Okay, so the goal is to interrogate nonlinear differential equations like this using some general tools, things that are going to work for the pendulum, but work for more complicated systems too. So what are some general tools? I mean, one of them certainly is the idea of linearization. Okay, so if you just care about the behavior of this system let's say in the vicinity of some particular point, I could take that equation and I could linearize it, make an approximation of sine using a line, okay? And then I get a linear differential equation which I could solve. And that's certainly one powerful tool that we're going to use for even complicated robots, okay? So it's good for local analysis. Most of the time. There will be nonlinear systems where the linearization is not informative. But in general, it's good for local analysis. But you might miss the global properties. You might miss the good stuff, right? And the other class of tools that I want to talk about today are sort of a graphical analysis. Okay, and so there's a great book by Steve Strogatz, which is one of the recommended sort of optional additional readings for the course. But if you like the kind of tools we're talking about today, this is sort of a one lecture channeling of Steve Strogatz's version of what he teaches a semester-long course on this stuff. It's a beautiful. I see the book right there. It's a beautiful course. It's a beautiful topic. Okay. All right. So let's do some graphical analysis. I want to start actually with even a simpler system. Okay. So. Start simple. Let's take the case of the pendulum still, but we'll do the overdamped pendulum, right? So basically I want to have a system where there's just a lot of damping in it. So what does that mean? I want B to be very large. We'll be more precise about that. In fact, really what I mean is I'd like B theta dot to be much bigger than the contribution from ML squared theta double dot over the trajectories of interest. Sort of some non-trivial solutions to the differential equation. Right, so why do I want that? I mean, you have an intuition about what an overdamped system is going to do, right? But procedurally here, this is going to make my life easier, right? So if I take my ML squared theta double dot plus B theta dot plus other stuff, right? I'm going to say this ML squared theta double dot plus B theta dot. If B theta dot is always way bigger than the ML squared term, then I can sort of approximate this term as just being B theta dot. Right? If I've got enough damping in the system, then I can sort of make that approximation. And this, if I finish the equation, now I've got U equals negative MGL sine theta, right? So now I have sort of a new governing differential equation for my system. And something big happened. Instead of having to think of it as a second order system, this approximation, I can think of it as a first order system, right? So my second derivative is now negligible in the dynamics. I can think of it really as just a first order dynamical system. And that's actually a general property of overdamped systems, right? So another classical example of overdamped system that you might encounter would be in fluid dynamics if you have very low Reynolds number fluid dynamics, where everything gets, well, it's still complicated, but relatively simpler than the full Navier-Stokes equations for low Reynolds number, because the system is so heavily damped that it starts looking first order again, right? So you can imagine, something swimming in honey, right? Then things start moving slowly, and really the dynamics of the fluid even become first order. Okay, so this is a general property, and it's just gonna take things and make it a lot simpler for us to start with the graphical tools. So it looks first order. I'm going to do one more simplification to make this sort of, just to ignore the complexity of it. So theta wraps around on itself every 2 pi. Let's ignore that for now. So just to be explicit about that, I'm going to just rename theta to x for now, just so we ignore the fact that it wraps around itself. I can separate out that complexity and we can put it back in later. Okay, so let's think about that differential equation, assuming that x at 2 pi is just a completely different thing than x at 0. All right, so my claim is that we're going to be able to, in a GIF, instantly with a simple picture, understand everything there is to understand about that differential equation, the long-term behavior, not the the time behavior, because that's still potentially hard. But that differential equation we can understand with a picture. All right, so how are we going to understand with that with a picture? Let's draw it. So bx dot was u mgl sine x. Let's just make a plot. Okay, so we'll plot x versus x dot. See if I can make effective use of colors here. Okay, so let's just say u equals 0 first. I'll plot the u equals 0 case. And it's going to look like, well, sine, negative sine, right? So something like this. Apologies for lack of artistic ability. It's going to look something like that, right? That's a sine wave, negative sine. I mean, what's the height? So let's just get it right. So the height is going to be mgl over b, right? Okay, so from this picture, there's a lot of things we can see very, very quickly. The first thing you can see is the zero crossings of that plot. Okay, so it's going to, this thing crosses 0 at 0, pi, 2 pi, right? I'll just circle them there. Okay, so what does it mean for that line to intersect 0? Right? If I'm in that position, if x equals 0, then x dot equals 0. Okay? So that's a fixed point of the system. If I'm in this place where x equals 0, x dot equals 0, the system's not moving. It's called a fixed point. All right? That's one of the first and most important definitions for nonlinear stability. These are fixed points. Okay, now these particular fixed points are at 0 and pi, 2 pi, 3 pi, right? So these are the two fixed points of the overdamped pendulum, the upright fixed point and the downward fixed point. Yeah? All right, so you can see also from these plots that these are qualitatively different fixed points, because in the vicinity of the fixed point, I can already also say more about the behavior. Okay? So you can ask about a natural question about fixed points is the stability of a fixed point, right? So if I were to be near that fixed point but not on that fixed point, if I start the system a little bit away, do I converge back towards that fixed point or do I move away, right? That's the question of stability of a fixed point. Right? So is this fixed point here stable or not stable? Can you see my? Yeah. It's stable. Right? You know that because it's the downward fixed point of the pendulum. You also can tell immediately from this plot that when I'm to the left of it, when x is negative, x dot is positive. Right? So I could sort of cartoon, maybe I'll draw an arrow right in like this. Okay? If I'm on this side of it, x dot is positive, and actually in this whole region, x dot is positive. And when I'm over here, x dot is negative, so my flow is going to go that way. So these are sort of the flow of the one-dimensional system. It can only draw the flow on the x-axis there, but that flow can completely describe the dynamics of the system. Okay, so this system is clearly stable because if I move away from it, I come back. And these fixed points here are unstable because of small deviation, and I'll move away from them over to some other fixed point, right? So maybe I'll fill in the stable fixed points. Okay. There's something else we can already do here, another relatively advanced concept in nonlinear dynamics. So for linear systems, stability is a global property of the system. A linear system is either stable or unstable. We'll talk more about that in a second. Nonlinear systems can have very rich behavior. So this point here is stable, but it's not globally stable. If I were to go all the way over here, I don't come back to this point. It's just got some region of stability, right? So in fact, those regions are, you can see from this plot immediately, the delineation of those regions, right? So there's some line here that goes through that unstable fixed point. Okay? And those are the boundaries of the stability region of that fixed point at 0, right? So in higher dimensional systems, those are going to be potentially complicated surfaces. In one-dimensional systems, they are always, the only place you can have a change in stability is at your unstable fixed points there, or you're at your fixed points, okay? Because you think about it, the stability changes when you cross 0, okay? The boundaries of a region of stability are called the separatrix of the system. Separatrix. They separate different regions of stability. Okay, and the region inside there, now I'm running out of colors here. I didn't think I'd use that whole palette. Okay, but that region here, yes, of course it works, yeah. That whole region there is the total region. Really, it's the region on that line, but I'm trying to be colorful here. So that set of states X is called the region of attraction of the fixed point of that at the origin. Sometimes it's called basin of attraction. Okay, and every one of those stable fixed points is going to have some region or basin of attraction. And I hope you enjoy the fact that you can just do this instantaneously with a picture here, because you'll never be able to have that luxury again. Sorry. But at least it lets us define and clearly what we're talking about, okay? We'll actually have pretty good tools for estimating those regions for complicated systems, but never so easy as this, right? Okay, so I think we understand pretty much everything there is to understand about the system when u equals 0. Okay, but what happens now if I start changing u? Yeah. It moves up and down, right? So that whole line moves up and down. If I just add u into the equation, that whole line moves up and down. What's going to happen to the fixed points? They start moving around, right? Can you see how they're going to move? Right, the fixed point at the origin, if I start increasing u, is going to be moving to the right. The fixed point at the top is going to be moving to the left. Okay, there's a critical point where if I put u equal to mgl, then something drastic is going to happen, right? Right? The fixed points go away. There will no longer be any fixed points of the system. What is that going to correspond to physically?
Can't stop.
Yeah, it starts going like this, right? So I actually, I brought a pendulum in one year, okay? And I actually said the words, "Let me demonstrate a lack of stability," okay? And there were supposed to be velocity limits on the pendulum, and I don't know how they got turned off, okay? But it was a dramatic demonstration, not to be forgotten, as I threw the pendulum, it ripped itself free of the stand and threw itself across the room in a clear demonstration of instability. Never to be repeated demonstration of instability. So this year I brought a MATLAB demo, yeah. Okay, but it's almost as good, I think, yeah? And a lot safer for me. You guys are all safe, you're like far enough back, but I was in serious danger. All right, so I think you guys have enough intuition about the pendulum that this is just a simple thing, but all right, here's a little pendulum with so far no damping. Okay, so it started from some initial condition. This is the theta versus theta dot over time. Okay, we're going to draw phase portraits in a second. All right, so let's give it some damping. Okay, now it's going to run out of energy and stand still at the bottom. That's what you'd expect. Okay. But that's actually not the system we've been thinking about yet. That's still taking a lot of time. What I want to be thinking about is when I've got a big B, right? And really it just goes straight down and the behavior is relatively boring, okay? But what happens then if I start taking my constant input U and I start giving it some constant torque? Then the fixed point's going to move, we said, right? Right? And there's another fixed point. Where is it on this picture? Where's the other fixed point? It's directly above it, right? Where the torque, so you can imagine the torque here holding up the pendulum against gravity. That's why the fixed point is where it is. There's a torque fighting gravity. And the other place where the balance happens is when that same torque is fighting gravity, directly above it. So I guess you can see it if I'm right here, right? That's the other place. But that's an unstable fixed point, so it's harder for me to show you with simulation. Okay, and relatively safer than what I did before. Let me demonstrate instability. I guess I have to turn that up even more. Boom, and this is what I did in class to great effect, and off it went, right? Just for grins, so in the real pendulum when I did the demo had additional details, right? So the real system, it was easy for me to set the friction to 0 in this model. The real system had friction. I had to model that friction with a quick experiment before I came down and invert it. So I had sort of a feedback cancellation that was taking out friction. The friction was changed a little bit as it went to higher speed. So basically, I was actually even adding energy on every time, and it was wild. It was awesome. But now it's safe. Okay. All right. So extremely simple system, but we got actually half a book's worth of definitions for nonlinear systems. Okay. I think it's really valuable. Now, one quick aside. I said that I wanted to think about the regime where B is big. You should think about units, right? So one thing I didn't write down, for instance, was I didn't write down B greater than ml squared because that's sort of intuitively what I want, but that's the wrong units, right? So just think about your units. There's units of theta is units in radians. Theta dot is radians per second. Theta double dot is radians per second squared, and so on and so forth. So really, if I wanted to make this comparison, I'd have to, this is missing a unit. I'd have to add some fundamental time constant, a square root of g over L or something to get the time in. And I said something about that in the lecture notes. But just be mindful when I'm not going to ask you, like I said, I'm not going to ask you ever to derive equations through the Lagrangian. but I'd like you to sort of have some physical, reasonable, be able to understand the equations when you're given them. Okay, does that make sense? Everybody happy with the over-damped simple pendulum? Okay, so now we have this graphical tool. Let's just think about maybe how that relates to the things we already knew about linear systems from your differential equations course, right? So linear systems are awesome because you can solve them, and actually you can approximate most really complicated systems as linear systems locally. So I mean, it's incredibly powerful, but maybe these plots sort of reveal how simple they are, right? So especially a first order one-dimensional system, really it can just be that. There's nothing else I can do for a linear system. So what would my plot look like if I were to plot x versus x dot for a linear system, right? So it's a line that would have gone through the origin if I was more talented, and with slope a, right? Okay, so what's that system going to do? Is that a stable system or an unstable system the way I drew it? Unstable, yeah. And so what's the criteria now for stability on A? A's got to be less than 0, right? So these are things you know from linear systems, but it's perfectly obvious from the picture, right? Right. So there's only a few things. Basically, you can and if it's stable, if I have a fixed point here, it's either globally sort of unstable or globally stable, and that's all the linear system can do, right? And if A is 0, then we call it marginally stable, right? But nonlinear systems can be much more rich, right? So I guess to write that, linear systems, its origin is the fixed point, the only fixed point, and it's either globally stable, unstable, or marginally stable. Right? But nonlinear systems are much more rich, right? So we can start talking about local versus global stability. And we'll see examples of both in pictures in the next few minutes. Okay, but we're also going to define. We're going to be more specialized. There's sort of more types of stability than just global. There's more useful distinctions than just that. Okay, we can also have multiple fixed points, as we saw in the last one. And actually, even as just understanding the behavior of the fixed points as you change parameters of the system is actually an exercise and often a very challenging exercise and rich exercise for these systems. And let's drill in a little bit. Let's talk about different kinds of stability. Okay, so let's start. Okay, so one type of stability is stability in the sense of Lyapunov, which is often abbreviated ISL, in the sense of Lyapunov. How many people know what Lyapunov stability is all about? All right, what's a good definition for Lyapunov stability? So that's a mechanism for proving Lyapunov stability. The definition is even simpler. You don't need a function to prove Lyapunov to define Lyapunov stability. So these are definitions that could be over a region or local or global. So what Lyapunov stability is one type of, so there's lots of things that could happen if I move away from the fixed point, right? Lyapunov stability is a particular guarantee. It says if you give me some epsilon, an epsilon ball, meaning that the distance between my initial conditions and my fixed point, I'll call x star the fixed point. Okay? If it is somehow less than or equal to this ball, or let's just say less than this ball. Okay, so if I start close to the fixed point, I'd like to remain close to this fixed point. Okay? Then I can give you a delta such that if I started inside epsilon, I'll always stay inside delta. Okay? If I give you a delta, I stay inside epsilon.
If you thought on delta,
yes. Okay. So yes. Good. So I felt wrong when I said it. Right. So if you give me a ball, good. Thank you, Ani. Then there exists an let me erase here. If you give me any epsilon ball that I have to stay inside of, right, then there exists a delta, thank you, such that if I start inside delta, then I'll stay inside epsilon for all of time. Okay, so the criteria is, I want to stay close. I want to stay epsilon close to this for all time. You should be able to choose an initial condition that's not the fixed point, but somehow close to the fixed point. That if I start there, inside here, I'll always stay. I'll never go more than epsilon away from that fixed point. Okay, so. For instance, in our pendulum example, we had a fixed point here. Is this fixed point stable in the sense of Lyapunov? Yes, absolutely. Because I could give you back, if you give me a epsilon, I could give you delta equals epsilon, and I'm all good. I'm only ever going to get closer in that case. Right? Okay. Another definition of stability is asymptotic stability. Which says if I start close, if a local asymptotic stability says if I'm starting close to the fixed point, then I will actually converge to the fixed point as time goes to infinity. Okay? So the limit as time goes to infinity of x of t equals my fixed point. Is that weaker or stronger than stability in the sense of Lyapunov? That's a stronger condition, right? The Lyapunov stability doesn't ever actually have to get there. It just has to not go away, right? And then the third one we'll use right away here is exponential stability. Which actually says that I'm going to go towards the origin at some rate. I'm going to go towards at some rate that's faster, that's bounded by an exponential. So the distance between x and my fixed point can be bounded by some exponential, c e to the at. Let's see. Less than 0. Yeah? So is exponential stability weaker or stronger than asymptotic stability? Right? It's not only got to get there, but it's got to get there at a rate. Okay? There's actually there's other bizarre things that nonlinear systems can do. You can even have finite time convergence, right? Or divergence. You can have nonlinear systems that will actually get to to the fixed point in finite time. And our time equals 3, I'm already there, right? Or divergence. Those are harder to see graphically, so we won't talk about them today, but maybe we might get back to them later in the class. Finite time escape is the divergence, right? Something that can actually go to infinity in finite time. These are things you just didn't have to worry about in linear systems, and nonlinear systems can throw all these things at you, all these curveballs. Okay, so these things are totally useful for the pendulum. Can we say anything about asymptotic stability in the pendulum? Is that fixed point asymptotically stable? Yes? Is it exponentially stable?
Yes.
How would you argue that it's exponentially stable?
You can linearize the system.
You can linearize the system. So for instance, a linear system we know has an exponential rate. If I don't even have to linearize the system. If I can just bound the system, if I can find some line that I could draw through here, right, so that the rate of convergence of the nonlinear system is faster than that linear system, then that's a proof, a sketch of a proof that it converges exponentially fast, right? Okay, so this doesn't just work for pendulum. This will work for any sort of nonlinear system. Here's another sort of fun nonlinear system. Okay, I don't know if you know, but my background's actually in a bit of background in neuroscience. So I actually worked with a neuroscientist. My advisor was a computational neuroscientist, Sebastian Sung. He still is a computational neuroscientist. He's gone to Princeton, but he's still a good guy. So actually, the way I started getting interested in this kind of stuff was learning about how feedback loops worked in neurons, right? So I don't know if you've seen neural network models, but one of the simple models of sort of a neural network is that you have some cell body of a neuron that maybe it has some nonlinearity in here, like a sigmoidal function of activation, and you have a bunch of inputs, sometimes with weights in them, for instance. W1, W2, W3, U1, U2, U3, let's say. And then some output, we'll call it Y. All right? And basically, these neurons will have a firing rate, let's say, that's a function, some nonlinear function of the input stimulation. Right? That's a common model of a neuron. All right? You'll see different types of sigmoids functions used, but it's very common to use these sigmoids for the firing rate. The one we'll use in a quick model here is the tanh function. So tanh, which you probably have no reason to be familiar with, but tanh of x is nice because it sort of asymptotes at 1 and negative 1. This nice sigmoidal property. This is tanh of x, and actually the slope here is 1, right at the origin. Okay, so this sort of feed-forward model of a neuron is a classical view of the neuron, and then for many years now, people have been excited about the idea of having feedback loops in these neural networks. Okay, so for instance, if this thing's connected back on top of itself, it has a self-connection, right? And then you end up getting, you have to somehow define, for this to make sense, you have to define some dynamics of this activation. Otherwise, you have some algebraic loop. Okay, so a more dynamic model of a neuron. Would be something, they'll call it something like this. The activation, the firing rate is tanh, but it's stimulated by tanh. But it has some sort of leak rate. So if you bombard it with input, its firing rate will increase, and then it's got a constant sort of leak rate, and that gives you sort of a first order dynamic model of the neuron. And in particular, one of the simplest models of a neuron, of a feedback loop in a neuron, is called the OTAPS, where it's really just a neuron in isolation with no external input, but just self-stimulation, just a simple feedback loop on itself, and you get something like this. Now it turns out, let's see if I can flip it open, this is a cool model because Sebastian was my advisor. He argued that this is one of the simplest illustrations of persistent memory, right? So, one of the prevailing theories of memory is that, certainly long-term memory is potentially changes in the connection strengths of those neural networks. But one of the prevailing theories of short-term memory is maybe that it's activation kept in some feedback loops, that you've got your neurons going and there's some activity that represents that memory. And so one of the simplest models of memory are these one neuron feedback loops. And we don't really know, they might know by now, but when I was in the lab, we didn't really know how common autopses, sort of neurons connecting to themselves, were in the brain. That's a hard thing to know. But certainly they happen all the time in a dish, right? So the way a lot of what we know about neuroscience is from culturing neurons out of a brain, taking them near the edge of death, having them sever all their connections, putting them in a dish, and then nurturing them back to life. And they grow new connections when everything goes well. And they're now in this weird environment where there's just a few neurons in a few small islands in a dish. And so they really want to connect to something. And so they end up connecting to themselves all over the place. And actually, it's fascinating to watch. As they come back to health, they actually start self-stimulating themselves and just have spontaneous activity, partly and persistent activity, partly because of these local feedback loops, right? So Sebastian got interested in understanding the simplest dynamical model of feedback and how it might be, modulated, how changes in the connection strengths of these synapses in the neurons, the connections in the neurons, can be understood with dynamical systems theory. Okay, so that's the equation we're going to use, and we're going to just plot it graphically, just like we did just now, and it's simple and beautiful, and we can understand everything about it. Okay, here we go. So if we plot tanh, right? So tanh looks like that, but now I've got negative x involved here. Let me see if I can just sort of in the background put my negative x in there, right? So that's my negative x, and then if I put my tanh on top of that, then what do I get? Let me draw it a couple different ways. First, as W, you can imagine as W gets bigger, that's going to compress this picture. It's going to make it a steeper sigmoid, right? And as W gets, as W gets bigger, yeah. So it's going to get bigger or more shallow or more steep, depending on as I modulate W. Yeah. So if I make W really steep, then I'll get a plot that looks like this, right? Something like that, right? The tanh modulated by negative x. And if W is very shallow, I can get a plot that looks more like this, right? So this is my W equals 3, let's say. This is W something, let's say half, okay? And now we can quickly understand the fixed points of this system, right? And how they change as a function of connection strength, right? So what are the fixed points of this system? If W is very large, well, I'm going to get a fixed point here, and fixed point here for the large W case. As W is very large, those are going to approach -1 and 1, just like we had before. What are the stable, are those fixed points stable, unstable? What do we got here? What's this one, stable or unstable? Stable. This one? Unstable, so I'll leave it unfilled in, okay. And this one's stable. Yeah? So actually, if you just, the simplest model of a neuron with self-excitation is that if you stimulate it, if you get it to start firing, it'll continue to fire until you somehow convince it to stop with some other stimulation, right? So with just a simple feedback connection that's got some connection strength, I can get stability in firing. I actually get bistability in firing. You can actually sort of stop it, you can turn it off or I mean, these are all sort of scaled, but you can imagine having this be sort of the off state and this being the on state, right? And if you have a whole grab bag of neurons in your brain that can have this, can lock into either off or on, then you've got the basic model of short-term memory. Yeah? And the cool thing is, the ability for this thing to lock into these bistable modes is parameter dependent, is connection strength dependent, right? So as I change W, as I decrease W in this case, then actually, again, my fixed points move, right? As this gets shallower and shallower, my fixed points are going to move inward until poof, they disappear. And then in the small W case, this becomes the stable fixed point here, and the others are gone, right? Okay, so you can tell, now this is the second time we've done the exercise, you can tell that understanding the way these fixed points move as a function of parameters is a useful exercise. And of course, there's a diagram you can draw for that too. That's called a bifurcation analysis, for instance. Okay, so if I plot the behavior of fixed points, and in particular, if I note the existence or disappearance of fixed points, that's called a bifurcation analysis. Shane? The bifurcation is when a fixed point comes into existence or is destroyed, let's say. And a bifurcation plot for that system, for instance, would be a plot, let's say, over my parameter W. I can plot the location of the fixed points of the system. Okay, so when W is small, or when W is even negative, seems like a bad idea, but if W is negative in that equation, then I had a fixed point at 0 and it was a stable fixed point. Okay? When W was large, we said we had two stable fixed points. We had one at positive 1, and we had one at negative 1. And then something interesting happens in between. It turns out the threshold where that fixed point is created or destroyed, remember I told you that tanh has a slope of 1 at the origin. So actually the critical point is when W equals 1. That's when this lines up exactly. Okay? So at W equals 1 here, this is where I have my bifurcation event. And I get two fixed points that split off like this. Okay? And actually, I still have a fixed point at the origin, but it becomes an unstable fixed point. So we draw this with a dashed line instead. Okay, now there's a whole field of bifurcation analysis for nonlinear systems. This is just one cartoon. It happens to be a fun one because this is called a pitchfork bifurcation, right? Oh, well, I don't know if it's even the most fun. There's all types of bifurcations out there with goofy names. If you Google, you'll find some of them. There's there's a blue sky bifurcation. There's saddle nodes are sort of conventional names, but there's all kinds of goofy names for nonlinear systems doing crazy things as their fixed points come together, explode apart. Okay. But this notion that fixed points can change or move as a function of parameters, that's a very nonlinear systems view of the world. Okay. Does that all make sense? I think you sort of, just from that quick coverage, I mean, you basically, if I give you a one-dimensional first order system, you can understand everything there is about it with just a few pictures. That's what I want you to take away, okay? And the second thing I want you to take away is that nonlinear systems can do all kinds of crazy things, even though you can understand them, but there's really a rich set of behaviors that you can see with nonlinear systems. The only thing you can't see is the specific time behavior of this. So we were able to sort of qualitatively say whether something's exponentially stable, but if it was finite time stable, it would be hard to see that in a picture, right? The specific metric time is a hard thing to get out of these pictures. But other than that, they're very, very rich. Okay, so let's do the 2D system. It follows on directly from this, right? So all right, so we're going to get back to our original ML squared theta double dot plus B theta dot plus MGL sine theta equals U. Okay, and you saw the pictures I plotted when I was simulating it. We drew what's something called the phase diagram. So in 2 dimensions, we really want to track both how theta dot and theta evolve with time. So we'll typically make our plots, theta versus theta dot. This is our phase portrait. And if you've had a good linear systems class, you've drawn phase portraits of these things and drawn eigenvectors and eigenvalues and characteristic equations on these in these phase portraits. It's a great view of the world. But we're going to do the nonlinear view of it. Turns out we can still do graphical analysis. It gets more complex. We won't be able to say quite as many things, but we can still see a lot of different things. Okay, so you know that this is a second order differential equation, but the way to think of it is really sort of as, you could think of it as 2 first order differential equations, right? I could always write it as in my sort of state space form. If I write a vector x which has theta and theta dot, and then I can write my x dot is theta dot theta double dot, then I can write 2 differential equations, right? So it's theta dot and it's 1 over ml squared, say u minus b theta dot minus mgl sine theta, right? So I can always write my second order system as 2 first order coupled systems. And if I were to replace this with x1 or x2, right, I could write that as purely as a function of x, right? x2 1 over ml squared u minus b x2 minus mgl sine x1, right? You know that. Okay. So now, where before I could just make a plot, if I put in one number x, I got out one number x dot. Here I'm really putting in 2 numbers, x1 and x2, or theta dot, and I'm getting back 2 numbers, which is theta dot and theta double dot, right? So the picture here is now a vector plot, right? So if I put in, for every theta and theta dot, that's sort of the input here, I get a vector out, which is my theta dot, theta double dot, if that makes sense. It's a 2-valued function. Okay, so these phase portraits are now vector diagrams, right? So this is, this coordinate is theta double dot, and this coordinate, theta dot, okay? Okay, so let's do the phase portrait of this guy here. Does that make sense, by the way? I've said that before and had it not land. Right, but it's just, you've got two values in, you get two values out, and I'm choosing, it's a personal choice. It's a free country. I'm going to draw it as a vector, yeah? And I'm going to try to convince you that that's a good thing to do, okay? So I can draw two numbers on a plot with a vector, and let's draw a bunch of these vectors and see if we can understand the gross system behavior, okay? So here we go. Let's do a special case where b equals 0 and u equals 0, just to draw that one first. So if I do theta versus theta dot, I'm going to use all the colors at my disposal here, okay? So first, let's just walk along this line. So now, well, what are my remaining equations? So I've got ml squared theta double dot plus b is 0. So it's just plus mgl sine theta, right? So theta double dot is just g over l sine theta, negative, yeah? Okay, so what's it going to look like? So as I walk along here, the x component is 0. Theta dot is always 0 along this line. So my vectors, as I walk along this line, the x component of the vector is 0. And the y component looks like negative sine theta, basically. Okay, so it's going to look a little bit like this. Yeah? What about if I walk along the other line here? Is theta dot is 0? What's it going to look like there? Sorry, if theta is 0, so now my y component is 0. So my y component of this vector is theta double dot. My x component is theta dot. You with me on that? Yeah? So as I walk along here, I just get theta dot is theta dot. So I get a line here. It looks like this, yeah? That would be a slope 1 line if I was talented, yeah? Okay, and then what happens in between? Over here, I get something that's got some of this and some of this. So I get a vector that's going down like this. Over here I get something like that. I get a combination of these things over here. Okay? And if I were to try to solve this system, if I were to start simulating it from some initial condition, let's say this would be starting at the bottom but with some velocity, then it's going to follow these vectors, right? Instantaneously it's going to move along those vectors, and it's going to carve out orbits of the system, which if there's no damping, are going to be closed orbits like this. Yeah? And actually there's going to be lots of them. They're not quite concentric, and that they should be more round than that. But well, so there's a fixed point here. Remember, there's a fixed point here, and there's another one over here. Right? Whenever theta double dot equals 0, whenever sine theta equals 0. So something special happens at that one. There's an orbit that goes directly through up to that fixed point. Okay? And what you get out, if you draw enough of these, there's actually another one that comes this way. So you get this freaky eyeball-looking thing. That's the famous canonical pendulum eyeball. Yeah? Over here you get orbits that look like this. Yeah? This is all just from plotting a few vectors and filling in some of the details. Okay, so this is the phase portrait of the nonlinear, undamped, no input pendulum. Yeah? So I said, and if I started here, for instance, which would be like this, then I drop it, and if it's undamped, it'll just go like this forever. And that is equivalent to going around. It's always going to go clockwise in these plots. It's going to go around in these circles, yeah? Okay. Is this fixed point at the origin stable? Is that stable? Yes or no? It's a bad question. You should catch me on that. It's not a good question. Depends what kind of stability, right? Is it stable in the sense of Lyapunov? Why is it stable in the sense of Lyapunov? If I start near it, if you give me some ball that I have to stay inside, I can definitely pick an initial condition or a set of initial conditions so that it'll never leave. Okay? So it's stable in the sense of Lyapunov. Is it asymptotically stable? No, right? If I start away from it, it will not actually go back to the origin. Right? So this is an example of something that has only one of those definitions of stability. Is it exponentially stable? No, if it's not asymptotically stable, it's not exponentially stable. Okay? Good. Now, if we want to do the same thing for the damped pendulum, right? Or even if I start adding u, then again these fixed points are going to start coming together, right? So I wish I could have two mouse cursors, but this fixed point is going to move this way. This one's going to move this way, okay? And these things are going to warp. Okay, I could make the same drawing, and I'll just draw it. I'll sketch it quickly here, but the same drawing for the damped pendulum, and a nicer version of it is in your notes. Okay, so this is still a straight line. That's not going to change. That's just every second order system is going to have that component. This one's now similarly not going to change. But what changes is the stuff in between, because I have some damping in here. I get vectors that have more sort of deceleration, okay? And the orbits that you'll get out are going to look like this. Right? That's my damped pendulum. And you can read it right off the vector plots. And you'll get the same sort of crazy behaviors, okay? But now this fixed point is asymptotically stable, okay? And in fact, so you still have an unstable fixed point over here, but things get much more complicated very fast. Okay. Now here's a really important point. So I wrote my equations here. We said that x dot is really just x2, let's say, and then 1 over ml squared. I could almost leave that out. That's not the important thing. U minus b x2 minus mgl sine x, okay, x1. Right, so that's what makes up these vectors. What happens now as I add u? What can u do to my vectors? Right, so I have a vector here. Can it change my y component? U has absolutely no impact on the y component of that vector. Right? Yeah, thank you. Yeah. Why? Yeah, so it has no effect on the x component of that vector. It has an effect on the y component of that vector, and only on the y component of the vector. So what you can do by modulating control is I can move that vector up and down. That's what your control gets to do. You get to shape this vector field, okay? So I mean, I don't know how to conjure this, but I almost want you to think of yourselves as, I don't know, Mickey Mouse in Fantasia or something, right? So you get to, you're the control designer, right? And you get to sort of pull up vector fields over here and push down vector fields over there, and you should just sort of, you should be dancing around, reshaping to the extent that you're capable of, reshaping this vector field, and there's constraints. You can only do it in this direction, right? You're not all powerful. You're still, I guess, an apprentice. I don't know. I didn't really mean for that to go that far. You have some limits to what you can do, but you get to reshape the vector field. And maybe if you have torque limits, right, maybe you only get to reshape it a little bit. Or maybe if you want to do it with just a little bit of energy, you want to have a sort of an efficient control system, then you get to do it a little bit, okay? And the name of the game, the name of the sort of control design game, is coming up with ways to modulate that vector field, potentially in a minimal way if that's what you like, right? To change the gross behavior of the system, to make it do what you want to do, but by just sort of tweaking that vector field. That's the picture that I want you to have in your head going forward, and that's the thing that's sort of really hard to do on paper, but that we're going to find really powerful tools to do algorithmically. Okay? This is where the computer scientists have something to say. Okay, we're going to find algorithms that if I specify high-level objectives, like I'd like to get to the origin, but in minimum time or with minimum control effort, and you give me even really complicated vector fields, I'm going to still be able to solve a numerical approximation of, optimally. I'm going to reorient the vector fields just like so, and be able to solve this sort of vector field exactly. When you get high-dimensional systems, then our tools are going to have to change, right? But always the name of the game is going to be, how do you take this vector field and move it around given the constraints? You can imagine now what underactuated is all about, right? So if this is a high-dimensional vector field now, let's say I have a robot with 4 joints. I have a plot that would be in 4 positions and 4 velocities. And let's say I have only 2 control inputs u, then the way I get to reshape that vector field is constrained in subtle ways, right? And so taking that same vector field and bending it to your will and making it do the right thing gets to be a harder problem. But if we can throw the right computational tools at it, we're going to see that there's still very, very satisfying solutions. Yeah? No, you in general, as a control designer, you're going to be able to choose u as some function, let's say of x. Yeah, absolutely. It's much more interesting. You could have function of time too, if you like. Yeah, and so you get to design that function. Yeah, so it depends. So there are algorithms that will make numerical approximations of the solution as a function of time to do that. Yeah. Sometimes time is very critical, and so we need to resort to approximations of the solutions to do it. If you have to get to the bank before 5 o'clock, you got to get to the bank. Yeah. Okay. So for simple systems, we can really understand the basic concepts of dynamics with a few pictures, right? But I really want you to get excited about the beauty of dynamics and understand that the class is really about algorithms for redesigning that vector field so that you can make a robot bird fly across the room and land on a perch or whatever you want to do, right? That's what the class is about, is working within those constraints to reshape your vector field.